In lesson 1, we looked at what a Mosfet is physically: the substrate, the oxide, the gate, the channel that forms under the right conditions. Today, we take a completely different step, but an absolutely essential one. We learn how to read a datasheet properly. I want to tell you something that, honestly, should be written on the wall of every lab. The datasheet is the electronics engineer's first weapon, not the textbook formula. The formula tells you how an ideal transistor should behave. The datasheet tells you how the specific piece of silicon you're holding actually behaves. Let's open SIHF640.pdf and walk through it page by page. Every Vishay datasheet has the same structure. Learn it once and you'll recognize it afterward across their whole portfolio. On the top of page 1, there's something called product summary. It's a tiny table that throws 4 or 5 marketing numbers at you: VDS, RDS, QG, QGS, QGD. For the IRF640, it says 200 volts, 0.18 ohms, 70 nanocoulombs, 1339. Wait, why do I call these marketing numbers? Because they're written short, without conditions, and they're designed to help you decide in 10 seconds whether this part makes your shortlist. They are not the numbers you use in a real calculation. The real calculation happens using the tables below, where every number has its test conditions attached. Below product summary, there are 2 blocks you need to love: absolute maximum ratings and specifications. The first tells you what you must never exceed. The second tells you what the manufacturer promises under stated test conditions. And then, on the following pages, there are the figures, the graphs that tell you the full story, the nuances a table simply cannot capture. Let's go through each. At the bottom of page 1, we find the absolute maximum ratings table. This is literally the red line of the part. Any excursion, even for a microsecond under bad conditions, can cost you the transistor. Let's read them together. VDS equals 200 volts. Maximum drain to source voltage when the gate is tied to source, so transistor off. If you reach 201 volts, you enter avalanche. The IRF640 is avalanche rated, meaning it can absorb a limited amount of avalanche energy, but this is not an invitation to push it. VGS equals 20 volts. Gate voltage must never exceed 20 volts. Why? Because the gate oxide is thin, a few nanometers. Push it past this limit and you punch through the dielectric. The transistor becomes a smoking resistor. ID equals 18 amperes at Tc equals 25 degrees Celsius, but only 11 amps at Tc equals 100 degrees Celsius. This is one of the single biggest traps in any datasheet. The big number on the front page, 18 amps, is only valid if you hold the case at 25 degrees Celsius. In a real circuit, the part hits itself and its current capability collapses. The practical recipe: always compute dissipated power, junction temperature, and then decide how much current the device can carry. We'll come back to this in the thermal lesson. IDM equals 72 amperes. Maximum pulsed drain current, low duty cycle, useful for transients. EAS equals 580 millijoules. Avalanche energy for a single pulse, meaning if the transistor is forced to absorb the energy of an inductive kickback and that energy is below 580 millijoules, it survives. Above? Probably not. PD equals 125 watts at Tc equals 25 degrees Celsius, with a D rating of 1 watt per degree Celsius. So at Tc equals 100 degrees Celsius, maximum dissipation drops to 125 minus 75 equals 50 watts. And here I have to be very direct with you, because it's a trap every beginner falls into. 125 watts does not mean 125 watts without a heatsink. That number assumes you keep the case at 25 degrees Celsius, which is physically impossible in free air. But the takeaway I want you to leave with now is real maximum power depends on what you have mounted on the transistor, not on what page 1 says. Junction temperature range -55 to +150 degrees Celsius. Beyond 150 degrees Celsius, the structure starts to degrade irreversibly. You see a pattern. Every limit depends on temperature. That's the central theme of any power MOSFET. Ignore temperature and your simulations will look pretty while the real part blows up on the bench. On page 2, we reach the bread and butter of the datasheet, the specifications table, split into static and dynamic, DC parameters and switching related parameters. Static section. Look at the first line. Breakdown VDS minimum 200 volts measured at VGS equals 0 and ID equals 250 microamperes. See the catch? That 200 volts figure means something only under those conditions. Gate shorted to source and a tiny leakage current. It is not the voltage at which the transistor works. It's the voltage at which, when you inject a small leakage current, the voltage stabilizes. A precise definition, and it explains why a round number like 200 volts needs half a page of footnotes. Next line. VGS, the threshold voltage, between 2.0 and 4.0 volts, measured at VDS equals VGS, ID equals 250 microamperes. Something that surprises many people. It's a range, not a single number. The datasheet says any IRF 640 you buy will have a threshold somewhere between 2 and 4 volts. If you need a precise threshold, you have a design problem. You cannot base your circuit on a nominal VGS. And another important detail, hidden in a figure later. VGS decreases with temperature, roughly 4 to 6 millivolts per degree Celsius. So at 100 degrees Celsius, the transistor opens at a lower voltage than when cold, critical for hard switched applications. RDS on equals 0.18 ohms maximum at VGS equals 10 volts and ID equals 11 amperes. This is the headline number. But again, conditions matter. If you drive the gate at 5 volts, the resistance will be significantly higher, maybe double. And it increases with temperature. See figure 4, which we'll reach in a moment. GFS equals 6.7 Siemens minimum at VDS equals 50 volts, ID equals 11 amperes. The forward transconductance. When the Mosfet is in saturation, used as a linear amplifier, 1 extra volt on the gate produces amperes on the drain. That's a big number. It's why power MOSFETs can deliver large currents with relatively weak drivers. Dynamic section. This moves us into switching behavior, which we will cover in later videos. For now, remember 3 key sets of parameters. CISS equals 1300 picofarads. COSS equals 430 picofarads. CRSS equals 130 picofarads, measured at VGS equals 0, VDS equals 25 volts, and 1 MHz. CISS is the input capacitance, what the driver sees when driving the gate. CRS is the Miller capacitance, responsible for effects we'll analyze in detail later. Be careful, figure 5 shows that these capacitances depend strongly on VDS. The values in the table represent only a single point on a curve. QG equals 17 nanocoulombs max, QGS equals 13 nanocoulombs, QGD equals 39 nanocoulombs. Total gate charge. This tells you how much driver current is required to switch the transistor within a given time. For example, if you aim for a 100 nanosecond switching time, the driver must supply roughly 0.7 amperes peak. That's not trivial. TD on equals 14 nanoseconds, TR equals 51 nanoseconds, TD off equals 45 nanoseconds, TF equals 36 nanoseconds, measured under very specific test conditions. RG equals 9.1 ohms. RD equals 5.4 ohms. VDD equals 100 volts. ID equals 18 amperes. Change any of these conditions and the switching times will also change. In particular, RG has a strong influence. Further down in the same section are the body diode characteristics, the intrinsic diode between source and drain, which exists naturally due to the vertical structure of a power Mosfet. Here, VSD max equals 2.0 volts and the typical reverse recovery time, TRR, equals 300 nanoseconds. For inductive loads, this diode becomes especially important. Tables give you points, graphs give you trends. Let's read the key figures of the IRF 640. Figure 1. Output characteristics at 25 degrees Celsius. Horizontal axis, VDS in volts. Vertical axis, ID in amps, log scale. The curves are parameterized by VGS, from bottom to top. 4.5, 5, 5.5, 6, 7, 8, 10, and 15 volts. What does it tell you? Two clearly different regimes. On the left, the curves are nearly vertical, the triode region, where the Mosfet behaves like a voltage-controlled resistor. On the right, the curves flatten out, the saturation region, where the current depends almost entirely on VGS, not on VDS. This is the fundamental DC map of the device, and we'll study it in Lesson 3. Figure 2 is the same characteristic at 150 degrees Celsius. Compare them. The hot curves sit lower. That's the visual manifestation of what we call negative temperature coefficient of drain current at high VGS. At high temperature and high VGS, the current drops. Good news for paralleling multiple MOSFETs. They self-balance thermally. Figure 3. Transfer characteristic. ID versus VGS at VDS equals 50 volts. Two curves, 25 and 150 degrees Celsius. Notice the crossover point, where the two curves intersect. Below that point, the current has a positive temperature coefficient. The transistor conducts more when hot. Above, a negative one. Designers using MOSFETs in parallel for audio amplifiers know they must bias above this point, otherwise they get thermal runaway. Figure 4. Normalized RDS on versus temperature. At 150 degrees Celsius, the on resistance is roughly twice what it is at 25 degrees Celsius. That must go into any loss and heatsink calculation. Figure 5. Capacitances versus VDS. CISS drops moderately. COSS and CRSS drop dramatically as VDS rises. At VDS equals 25 volts, CRSS is about 130 picofarads. At VDS equals 1 volt, it can be 5 to 8 times larger. This explains why switching is slower at low VDS and faster at high VDS. A counterintuitive effect we'll exploit in Lesson 8. Figure 6. Gate charge. One of the most important figures for driver design. Horizontal, charge injected into the gate, in nanocoulombs. Vertical, VGS. It's not a straight line. There's a Miller plateau, roughly around VGS equals 5 volts. In that plateau, every coulomb you pump into the gate goes into the gate drain capacitance, not into gate source. VGS simply stops moving until CGD is fully discharged. That's the Miller plateau, and it's the bottleneck of switching. 3 curves for 3 VDS values, 40, 100, and 160 volts. Notice how the plateau is longer when VDS is larger. Figure 8. Safe Operating Area, SOA. The map of all VDS, ID, points where you're allowed to operate the transistor, parameterized by pulse duration. For short switching pulses, you get a generous rectangle. For DC, the area shrinks dramatically. The top left limit is RDS on, the bottom right limit is VDS breakdown, and the diagonals in between are thermal and second breakdown limits. Figure 11. Transient thermal impedance. Tells you, given a power pulse of duration T, what junction temperature rise do you get? This is the fundamental equation of any thermal stress calculation in switching. So far, we've been reading the data. Now, let's actually use the model. Manufacturers provide SPICE models for their MOSFETs, and for our simulator, QSPICE, we're in luck. QSPICE includes a built-in model specifically designed for vertical power MOSFETs called VDMOS. This is not the simple level equals 1 model you may know from introductory courses. That one is far too idealized for power devices. VDMOS is essentially level equals 1 plus a body diode with reverse recovery plus a nonlinear Miller capacitance CGD that collapses with VDS plus separate parasitic resistances on the drain, source, and gate. In other words, exactly the effects that actually matter in a power MOSFET. Now I'd like to propose a very simple experiment, one that at a glance shows almost everything we've discussed in this lesson. In QSPICE, I built the circuit you see on the screen. We have an IRF with the drain connected through a 1 ohm resistor to a fixed 25 volt supply V1. The source is grounded. On the gate, I place the second source, V2, which I sweep from 0 to 10 volts in steps of 50 millivolts. So what are we actually doing here? We are asking the transistor a single question, over and over again for each value of VGS. How much current will you let through? And the answer, on the vertical axis, is the drain current. The 1 ohm resistor on the drain has only one purpose: to limit the maximum current to a reasonable value. Without it, the simulator would happily report more than 50 amps at VGS equals 10 volts, which is not physically realistic. We hit run and we get this curve. Let's read it together, because in this single plot you can clearly see all three operating regions of the MOSFET. From 0 up to about 4 volts, the curve is flat at 0. The channel hasn't formed yet. The transistor is in cutoff, completely off. This is the threshold region. Between 4 and 7 volts, the curve rises steeply, almost quadratically. Here, the transistor is in saturation, behaving like a voltage-controlled current source. A small change in VGS produces a large change in ID. The slope of this region, if you measure it, gives you the transconductance, around 7 Siemens, exactly as stated in the datasheet. And above 7 volts, this is where it gets interesting. The curve flattens out at about 21 amps and stops increasing no matter how much we raise VGS. Why? Because the transistor has entered the triode region. It now behaves like a resistor of about 0.18 ohms, and the current is no longer determined by the device itself, but by the external circuit. So, in a single graph, we have cutoff, saturation, and triode, the three fundamental operating regions of the MOSFET, which we'll study in detail in the next lesson. And most importantly, the shape of this curve closely reproduces figure 3 from the Vishay datasheet.